Okay, hi folks. So this is lecture 32. This is not a live stream lecture. We had some issues with setting up the live stream this morning. So instead, this is a pre-recorded lecture, and then I'll upload it in the afternoon. And in this last chapter, we want to go back to this fundamental question of how do you know that the solutions that you've been developing over the last few weeks, solutions for the heat equation, for the wave equation, for Laplace's equation, how do you know that these solutions are unique? How do you know that, for example, the Fourier series you found is the only solution of the problem, and that there are perhaps other solutions that you just didn't have the techniques for, okay? And the main answer that we're going to find from this chapter 19, is that the solutions that you have are indeed unique modulo things like constants and under certain weak assumptions, okay? These are the problems that we're going to be considering in today's lecture. We're going to be considering uniqueness for the heat equation. So this is the standard heat equation on a line. You can also prove, if you like, uniqueness for other geometries, but it's efficient for us to demonstrate the case for a line. This is going to be the heat equation for a line, and we're going to assume the line runs from 0 to L. So this is like the heat distribution in a bar. It's going to have some specified initial condition, u of x0 is equal to f of x. And it's going to have different kinds of boundary conditions, and you have to be able to learn how to prove uniqueness for all the different kinds of boundary conditions, mainly Dirichlet, given by this D condition. So I set the temperature of the bar at either ends. Neumann, which is the derivative of U, and you set the derivative of U at the two ends, either to be a G0 and a G1. Or a mixed boundary condition, where at x equal to 0, you set it to be some constant times u plus some constant times ux plus h0. So it's a mixture of Dirichlet and Neumann conditions. Okay, we're not going to be covering this one today. This is in fact in your problem set questions. And for the most part, we're going to consider these to be constant. So you could change this T0 or this T1, so you can set it so that the heat at the boundaries is a function of time, but we're going to consider it to be constant. And so what we want to do is we want to prove that if we were to find solutions of this problem, for example, the heat equation with Dirichlet conditions, or the heat equation with Neumann conditions, or the heat equation with mixed conditions, then this solution that we found is unique, okay? And the basic idea, there are many ways of doing this kind of demonstration. We're going to be using sort of an algebraic manipulation way, and in doing so, we're going to come up with a so-called energy of the problem, okay? So what we're going to do is we're going to first assume that you have two solutions. Let's assume that you have a u and a v. So let's let u and v be distinct solutions. In fact, I'm not going to write distinct here. Let's just say two solutions, and then we'll just show. Okay, and let's set w of x and t to be equal to u of x and t minus v of x and t. Okay? And the goal is basically that if u and v are to be distinct, then w here would have to be non-trivial, right? If it's trivial, then u and v are identical. Trivial meaning 0. So what you do is you stuff this into your governing system, and then you find out what equations w satisfies and what boundary conditions w satisfies. We're going to do the Dirichlet condition first, then we'll do the Neumann condition, and then we'll leave the mixed condition, either for your problem sets or for a future lecture. Okay. So let's put this into this equation here, and you notice that if you put this into that equation, so I put this into the PDE, and I have WT is equal to UT minus VT. So this is just from taking the time derivative of this quantity, but I know that U of t and V of t are given by that PDE because I've assumed that there are solutions. So this is basically kappa times uxx minus kappa times vxx, okay? And then this is basically kappa times wxx, just the two x derivatives of w. So in other words, wt must solve the heat equation itself, so let's erase that, and then we'll write it here again. So this is wxx. Okay. So in fact, this is nothing more than by property of the linearity of the equation. The equation is linear, therefore having two solutions, u and v, w itself must be a solution. Okay, so the next thing we need to do is we need to impose this initial condition, but the initial condition of u of x0 minus v of x0 is just f minus f. So w of x and 0 is u of x and 0 minus v of x and 0, which is just f of x minus f of x, because u and v satisfy the same equations, and therefore this is equal to 0. So let's erase that. And then we have 0 here. And then finally, I have the two Dirichlet conditions. And u and v must be both t0 and t1 at their respective boundaries. So w of 0 and t is equal to u of 0 and t minus v of 0 and t. So it's t0 minus t0, so that's 0. And similarly for the other end, it will just be w of l and t is equal to u of l and t minus v of l and t, and hence t1 minus t1, and hence 0. So w of l and t is equal to 0. And there's the system of equations that we'd like to solve. Okay? Now, this thing here, you could imagine it to be essentially the W is the heat distribution in a bar of length L that starts off with an initial heat of 0 everywhere, and the initial heat of, or initial temperature, if you like, of 0 at the left end and 0 at the right end. So it makes sense, it makes intuitive sense that the only solution to this, if you imagine a bar which starts off at 0 degrees everywhere and is 0 degrees on the left and 0 degrees on the right, it makes sense that the bar is going to be basically 0 degrees for all time, right? That's essentially what we want to prove, that the only solution to this problem is the trivial solution, w equal to 0. If we can do that, if w is equal to 0, that would tell you that u is equal to v, and you have uniqueness. Okay, that's the basic idea. Okay. So what we're going to do is we're going to take this PDE, and then you're going to manipulate it. And the aim is essentially to manipulate it in a way that you can find a certain quantity which is conserved, or which is positive, or which is negative. Some sort of quantity that you're able then to make certain conclusions about. And that quantity turns out to be the thing that we often associate with the energy of the problem. Okay? So I'm going to take this PDE, I'm fine now to erase both of these conditions, and I'll show you the algebraic manipulation that results. Okay, so you're going to take the PDE, Wt is equal to kappa times Wxx, and you're going to multiply both sides by W. Okay, so now you have WWT, and we'll do it on the same line, so in fact, I'll do it over here. I have Wt is equal to kappa times Wxx, and then you're going to multiply both sides by W. Okay? And then what you notice is that you can rewrite this left-hand side as a derivative term. Okay? So you can rewrite this left-hand side as the derivative of ddt of 1/2 W squared. Because then the 2 comes down, you have W times Wt. And I'll leave this as kappa times Wxx. Okay? The next thing you're going to do is you're going to integrate both sides with respect to the entire domain. So I'm going to take an integral from 0 to L of this left-hand side. Make sure I have enough space here. And this is integral from 0 to L of kappa times Wx dx. Okay? Good. So the next thing you want to do is you want to rewrite this. Missing an x there, so this is W times Wxx. Okay, so the next thing you want to do is you want to do a product rule with this left-hand side. And so you'll notice that if I take ddw, ddx, of Wx, okay, then I have basically wx times wx, so that's wx squared, plus w times wxx, like this, okay? So this here appears on the right-hand side of your integrand, and so this allows you to move this left-hand side, this wx squared, over to the left-hand side, and then substitute that form into that integral. That's exactly what we're going to do. So let's erase this quantity here. We'll move the kappa out to the left-hand side. And then we're going to have a ddx of a wwx minus a wx squared. Let's make sure we put everything into brackets like this, and a dx. Okay? Good. So now you're free to integrate this first term because this is just the integral of a derivative, and then we'll leave the second term. So we're going to rewrite the next line. You're also free to move this dx out to outside of the integrand, because the integrand is just integrated in x. Okay, so let's move the dt out. And I have a 1/2 w squared dx. And then we're going to integrate out of this ddx. So we have a kappa times a wwx. Evaluate from the left and from the right. Okay. And then we're going to have a minus kappa times the integral of wx squared. So minus kappa times the integral of wx squared dx. Okay? Okay, good. So firstly, this quantity on the left-hand side, for reasons that it's going to become quite clear, I'm going to call this to be the energy. So I'm going to call this thing here to be E of t. Okay? The next thing I'm going to do is I'm going to impose the boundary conditions on this quantity here. So in order to evaluate this quantity here, you have to take w at the L endpoint, and then subtract w at the 0th endpoint. But you know by the boundary conditions that w at the L endpoint is equal to 0, and you also know that w at the 0 endpoint is equal to 0. We wrote the boundary conditions, the Dirichlet conditions, using this quantity here. So you remember that w is u minus v, so it's t naught minus t naught, and so this is 0 at either end. So in fact, this term here is equal to 0, because w of L and t is 0, and w of 0 and t is 0. In other words, now you're left with some conclusion on the derivative of this E of t. So let's rewrite that up here. So at this point, you've concluded that E prime of t, this is now just a regular derivative. It's not a partial derivative because this here is just completely a function of t because you've integrated out the x. This is now equal to minus kappa times the integral from 0 to L of wx squared dx. And I was missing a 0 and an L here. Okay? Good. Okay, so now this thing here, you want to make a conclusion of what is going to be E of t based on what you know about the derivative. Okay, now this thing here, this integrand is the integrand of a squared number. So this part of the integrand will always be positive, and by assumption, this kappa, this thermal parameter kappa, is always going to be positive as well. So you're going to then conclude that this has to be less than or equal to 0. So E of t is non-increasing. It's non-increasing, or if you like, it either has to be decreasing or staying constant. So now you're going to use the fact that you're going to say note that at t is equal to 0, what is the energy at time t is equal to 0? Well, let's just put it in. I know that E of t is defined to be the integral of 1/2 w squared dx from 0 to L. And so I can just freely put in t into this because this x is integrated out, you see. So this is 0 to L of 1/2 w of x and 0 squared dx, like this. Okay? So just to be more correct, you should write a little bar here and put in t is equal to 0 just to emphasize the fact that you're evaluating this at t is equal to 0. Okay? But w of x and 0 is equal to 0. The bar initially starts off at 0 temperature. So this is 0. And you're left with the conclusion that the energy starts off at 0. Right? Makes sense. A bar which has 0 temperature should have 0 energy to begin with. Okay, so now you are ready to make the final conclusion. You've concluded that E of t is non-increasing, so it either has to be decreasing or remaining constant. You've also concluded the energy has to start off from 0. And finally, one other conclusion that you can make is that the energy has to be strictly greater than or equal. So it has to be greater than or equal to 0. The energy has to be greater than or equal to 0 because it's the integral of a squared quantity. Okay, so let's write down those 3 conclusions. So the first thing you've concluded is that E prime of t is less than or equal to 0. The second thing you concluded is that E of 0 is 0. And the third thing that you concluded is that E of t is greater than or equal to 0. Because this is the integral of a squared quantity. So from here, you conclude that E of t is identically 0. The only function that is decreasing or may remaining constant, but beginning from 0, but is always greater than or equal to 0, has to be 0 itself. So E of t is identically 0 for all t. Okay? And you're almost done. All you have to do now is make a final conclusion on what w is, right? Okay, so if E of t is identically 0, then the integral of 1/2 times w of x and t squared dx from 0 to L has to be equal to 0. Okay, because this is what E of t is. So here you conclude that basically w is identically 0. Okay, so the energy has to be 0 for all t, and this tells you that this quantity is equal to 0, and the only way you have the integral of a squared quantity equal to 0 for all time is if that quantity itself is identically equal to 0 for all t and for all x. Okay. Good. So this is it. This is the proof of uniqueness for the Dirichlet problem. Okay, so let's just recap what we've done. We first assumed that you have 2 solutions, a u and a v. We subtracted those 2 solutions and defined the w to be the difference between the 2, and our goal was to show that this w was equal to 0 for all time and for all x within the interval. Then you went and wrote down the equations that w satisfies. It satisfies the heat equation. It satisfies 0 Dirichlet conditions. These 2 conditions are 0 on either ends, and it satisfies a 0 initial condition. And then you began doing some tricks, some algebraic tricks. You start off with the heat equation, you multiply both sides by w, and then integrate both sides from 0 to L. You rewrite the left-hand side so that it's a derivative of some quantity which you call an E, and then you manipulate the right-hand side so that you're able to use these boundary conditions. And in doing so, you're able to come to the conclusion that this quantity, this E of t, always has to be less than or equal to 0. Steps 2 and 3 are just steps in which you're looking at the form of that energy. So in step 2, you substitute t is equal to 0 and you use the initial condition, and you conclude that the energy has to start off from 0. And then step 3 is you're looking at this quantity here and noticing that that quantity always has to be greater than or equal to 0. Items 1, 2, and 3 allow you to conclude that the energy has to be 0 for all t. And then finally, you're able to write down that this squared quantity is equal to 0, and the only way you have the integral of a squared quantity, which is equal to 0, is if that quantity itself is equal to 0. Okay, that's it. So now you're ready to try it again for the Neumann condition, and then finally for the mixed condition. But for the Neumann condition, it's exactly the same as for the Dirichlet condition, with the slight difference being that there's a step in the proof in which you use that particular boundary condition when you've rewritten the right-hand side of that integral, and that step will be slightly different. It's going to be very, very similar for the mixed condition, but there's a subtlety of what happens if A0 and B0, whether you're able to make the same conclusions depending on the signs of A0 and B0. But that's an interesting twist of the problem that I hope either you'll do in your problem sets or we'll do together. Okay. So I'm going to end the lecture by doing the Neumann condition, and you're going to see just how simple it is based on the Dirichlet steps that we took. Okay. Okay, so we're going to do it quite quickly, and we're going to do it quite efficiently. Let's set W to be U minus V. So I'm going to let W be equal to U minus V. I substitute this into these equations and those conditions, assuming U and V are solutions, and I come up with the conclusion that WT has to be a solution of the heat equation. I come up with the conclusion that W at x and 0 has to start off from 0, and that W of 0 in t has to be 0, which is the same as W of L in t. And I made a mistake here. This is a Neumann condition. Good. Now you're going to take this WT equal to kappa WXX and then just manipulate it, okay? Using the same steps as we did before. Multiply both sides by W and then integrate. So let's erase this. Let's multiply by W and then integrate. So let's rewrite the left-hand side here as a derivative. So this is a ddt. One half W squared. And then we're going to rewrite this right-hand side using the product rule. So we're going to notice that ddx of WWX is WX squared plus WXX. Move the WX squared to the left-hand side and then substitute the left-hand side, the new left-hand side, into this integrand. So this will become a ddx of WX minus a WX squared. And then let's put a bracket dx. Okay, now you're free to integrate out of this first integrand. And we're going to rewrite this here as E prime of t. So this is going to be E prime of t if E of t is this integral here, so we'll write that at the top. 1/2 W squared dx. So this is E prime of t equal to kappa times WWX kappa times WWX from 0 to L minus kappa integral 0x WX squared dx. But now you get to make the conclusion of what this term has to be based on the Neumann condition. I know that Wx at 0 is 0, and I know that Wx at L has to be 0, so this has to be 0. That disappears. And I'm left with the same conclusion as I had for the Dirichlet problem, that the energy is such that the derivative of the energy, E prime of t, is equal to this negative squared quantity. And so therefore, E prime of t has to be less than or equal to 0 for all time, because this is equal to the negative of a integral of a squared quantity, which is always, the integral of a squared quantity is always positive. Okay, so at this point, we have the first of the three conclusions we wrote down before. We have the fact that E prime of t has to be less than or equal to 0. We also have the second conclusion we wrote down before, which is that E of 0, which is the integral of 1/2 w of x and 0 dx squared from 0 to L, has to be equal to 0 because w starts off at 0. That was one of the conditions we wrote down for that equation for w. And then finally, we know that E of t has to be greater than or equal to 0. Why? Because it's the integral of a squared quantity. So it has to be greater than or equal to 0. So at this point, you're able to conclude that with item 1, item 2, and item 3, that you have the fact that E of t has to be identically equal to 0 for all t greater than or equal to 0. That is the only function that satisfies those three conditions. And so therefore, you're left to conclude that the integral of 1/2 w squared dx has to be equal to 0 for all t. And the only way that can happen is if that integrand itself is identically equal to 0. And so therefore, u of xt is identically equal to v of xt, and solutions are not unique. Okay? That's the end of both now the Dirichlet proof and the Neumann proof, and you have to do the mixed proofs yourselves, or again, we might pick that up in a future lecture. Okay, we're going to keep it nice and short. This lecture, just the heat equation. Next lecture, we're going to do the wave equation. See you soon.